let's sum up with an overview of some of the things that we found in this kind of more theory-minded lecture, where we proved a few lemmas that hopefully shed some insight into this probability, the stationary distribution of Markov chains. And kind of the two main sort of things that we were able to show was that if a Markov chain somehow happens to stumble on its stationary distribution, it stays there. And sort of maybe a different way of saying that is if a system, a Markovian system, reaches its equilibrium, then it stays in its equilibrium forever. And the second finding was that if a Markov chain finds some distribution to settle on, right? And then the first item is sort of mandated that it stumble on its stationary distribution. In the second item, we're saying, well, what if it just finds some distribution to follow eventually? Well, if it does that, then that distribution has to be the stationary distribution. That was the conclusion of the second main result, the second lemma. So that potentially raises more questions than answers. One of them is, does the for example, does that limit exist, right, in that second lemma? And I think I mentioned that that's not the case. Let me give you a quick kind of counter example. The counter example is a classic one based on two states, x and y, with what are essentially deterministic transitions, probability transitions between the two. And so now we can look at the k-step transition probability and find out that it's got to be either 1 or 0, but that will depend on k, right? If I start at x and I can move to y in one step, but I can't move there in two, because on the second step I'm brought over back to x, and so on and so forth, right? I can get to y on 3 but not on 4, and so on and so forth. And so this k-step probability had to be 1 when k is odd and 0 when k is even. And so that limit then that we're questioning a little bit now is essentially going to oscillate between 0 and 1 over and over and over. Right? It's going to just move around and never actually converge anything. And kind of that's the bad news. The good news is that this is essentially the worst thing that can happen, right, to break that limit and make it not exist. So this notion here of kind of the deterministic pattern, right, moving around in a cycle is called periodicity, and you might have come across it in 160A. And it kind of is essentially speaking, like not completely is not completely accurate, but kind of brass tacks here is that the periodicity of Markov chains is what's going to ruin this limit there, and removing it is going to recover it in kind of with a few caveats. And the other kind of piece of good news is that one way to get rid of periodicity is simply to add a self-transition. And so adding any self-transition like this, let's say this is a probability epsilon, and I would make this a probability 1 minus epsilon. This small change would make this chain no longer be periodic, and therefore limits like the one above are much more easily to establish. Okay, so that's that part is going to be easy. The second part is, does the stationary distribution always exist? And that's a harder question. I'll try to walk you through the proof. It's not. I think the statement is there in Ross without a proof, and we'll see if we can kind of tie some concepts together in a nice way that also shows you how to actually prove a statement like this. The answer is no. The stationary distribution does not always exist. There are again some good news. So let's see. Some good news are that when the state space is finite, when the state space S is finite, pi always exists. And we can kind of prove it pretty quickly. So one thing to do is when this is finite is we can set the size of this state, this set, right? This is just the number of elements in the state space. Let's say we make this to be n. Our global balance equations in that case can be written in matrix form, like this. So, and hopefully this reminds you of something from 160A, right? These are, maybe you didn't call them the global balance equations back then, but this is global balance, and hopefully you can connect sort of the notation I had using a sum with this matrix setup. So this right here is a matrix of one-step transition probabilities. So this is a matrix with entries P, X, Y, where X and Y are elements of S, right? And so this is the Xth row and the Yth column of this matrix, the entry in the Xth row and Yth column. And this pi is just the stationary distribution thought of as a vector. So here pi is equal to a vector pi 1 all the way through pi n, which is the size of the state space. And I wrote it as a row vector because that's how it multiplies the matrix, right? And so hopefully you can verify that it's the global balance equations, and also recognize that that in this kind of system, right, you have n equations and n unknowns, and therefore the solution is always going to exist. But that should also point you to the next question, which is the stationary distribution unique? And that's not going to be true, right? It's going to be unique when this matrix has all rows or all columns linearly independent, right? So that's a notion from linear algebra that hopefully you're familiar with, right? But and as far as kind of recognizing when a solution is unique, right? When all columns are linearly independent, the solution will be unique, and when not, then it's not going to be. And let me give you an example of when the stationary distribution is not unique. So an example of when the distribution is not unique would look something like this. This is a 3-state Markov chain, and it's very simple, but you can design all sorts of complexity around it just using this basic idea. I have a state x, and with probability p I transition to a state called delta 1, and with probability 1 minus p I transition to state delta 2. And you'll easily be able to see that there are two stationary distributions. One of them, let's call it pi 1, has pi x and delta 2 equal to 0, but pi 1 of delta 1 is equal to 1, right? And so the idea here is that we moved in this way. Oh, and I forgot, there are two self-transitions with probability 1, right? So these are, the delta is usually used to denote what's called an absorbing state, which is what these are. And so there are two absorbing states, and once you move a transition from x to delta with probability p, you'll always stay there, right? So once you hit a stationary distribution, you'll always stay in it. And the same thing happens here, but with probability 1 minus p, you go to delta 2 and then stay there. And so this is one of the stationary distributions. I call it pi 1. And to get pi 2, you simply flip the indices here. So pi 2 would stay in delta 2. Backing up to the question does the stationary distribution always exist? We saw that, showed once again that it seems to exist in finite state Markov chains. There's a good example of a Markov chain to know about when the stationary distribution, or for which the stationary distribution does not exist. I'll quickly give you this example. It's called the random walk on the integers. So z with this crossbar usually denotes the integers, and this is all it's going to be is a process defined as sk, which is a sum from, let's say, I equals 1 to k, and these are going to be random variables ci. Each ci is going to be an element of either -1 or +1, and they're going to be IID. Right, so these are going to be independent, identically distributed random variables, and we're going to sum them. And hopefully you can show that that this is indeed a Markov chain. It's a random walk on the integers because it moves on the integers. We start with 0, right? 0 things in the sum, and as time, right, k moves forward, this s is not the state space, right? This is just the usual typical symbol used for a random walk. And you're moving, right, either 1 to the left or 1 unit to the right, and just kind of moving around randomly, stumbling right on this integer lattice there. So this is why do I bring up this example. It's an example of when the stationary distribution doesn't exist, and you can try to kind of think about how that squares with your kind of notion of, say, the second lemma, where we assume some limit, right? Why isn't that in this case this this chain is just not able to find anything to converge to in terms of a stationary distribution? So the state space here, right, is the integers, which is an infinite set. So that's that's kind of the big distinction going from finite state Markov chains to infinite state ones. Let's see. So finally, we have this concept of reversibility that we discussed a little bit, and that's going to be kind of a big component of the second homework. And what you'll show is that reversibility is essentially tied to the notion of random walks on networks. So this is one such example. You have a random walk on the integer lattice, but in general, you can have random walks on more complicated networks. So the integers are essentially a network that looks like this. Right, so these are the integers -2, -1, 0, right, and it goes out this way and that way, right, all the way, right. So these are all the numbers, right, natural numbers listed, and the transitions between them, right, goes this way or that way, right. You can walk to any adjacent neighbor because you're moving in steps +or -1. And a random walk on a network will in fact have any other arbitrary number of states, and they'll be connected in all sorts of ways, right? A very kind of general way that you could connect it to, and essentially the random walk will move right all over these states in kind of an arbitrary way, and we'll see why why that is in fact equivalent to the concept of reversibility. But they'll have to wait for a couple of lectures.